Introduction to Basic Data Analysis in an Undergraduate Physics Laboratory. In physics, simply getting a number from an experiment is not enough. A measurement is truly meaningful only when we can also state its uncertainty. Think about it. Our ultimate aim is not just to pinpoint a single value, but to define a range within which the true value of a physical quantity likely lies. For instance, if we are measuring the acceleration due to gravity, g, just saying g equals 9.8 is a rather poor result. A much better, and more scientifically sound, result would be something like g equals 9.81 plus or minus 0.05 meters per second squared. This tells us not only the value, but also how confident we are in it. This lecture is designed to give you the fundamental tools to determine these uncertainties correctly. We will also touch upon the important concepts of precision versus accuracy, which are crucial in understanding experimental results. Experimental uncertainty, something we will encounter in every lab session, generally falls into two main categories. First, we have random uncertainty. This comes from those unpredictable little fluctuations. For example, maybe there are tiny variations when you are reading an analog scale, or your reaction time with a stopwatch is not exactly the same every trial. Electronic noise in a circuit is another common culprit. The good news here is that we can usually minimize random uncertainty by taking more measurements. The more data, the better our average becomes. Then, we have systematic uncertainty. This one is more like a consistent glitch, a fixed offset or scaling error that affects all our readings in the same way. So, just repeating measurements will not make it go away. Think of using a miscalibrated thermometer that always reads high, or consistently viewing a meniscus from the wrong angle. Forgetting to factor in wire resistance in a circuit is another example. It is really important to sniff out these systematic issues because they need a different correction strategy. When we report our experimental results, it is really important that the numbers we write down accurately reflect how precise our measurements are. We cannot just write down all the digits our calculator might show. There is a general rule we follow for this. First, we look at the uncertainty we have calculated. We will usually round this uncertainty to 1 or perhaps 2 significant figures. For example, if our calculated uncertainty, let us call it delta L, is 0.4385 centimeters, following the rule to round to one significant figure, as shown in the example on the slide, this becomes 0.4 centimeters. Now here is the crucial part. We then round our main measured value to the same decimal place as this rounded uncertainty. So if our calculator showed the length L as 85.34721 centimeters, and our uncertainty delta L is rounded to the tenths place, which is 0.4 centimeters, we then round the value of L to the tenths place as well. This makes L approximately 85.3 centimeters. Therefore, the correctly reported result would be L equals open parenthesis 85.3 plus or minus 0.4 close parenthesis centimeters. This ensures consistency between the value and its uncertainty. When we repeat a measurement capital N times, we get a set of data, x1, x2, up to x capital N. To analyze this, first, we find the mean, x bar. This is simply the average of all measurements, and it is our best estimate of the true value. You calculate it by summing all values and dividing by capital N. Then, to understand the spread of our data, we use the standard deviation, sigma x. This value quantifies how much individual measurements typically differ from the mean, essentially giving us the uncertainty of any single measurement. Most importantly for our final result, we calculate the standard error of the mean, sigma x bar. This is the standard deviation sigma x divided by the square root of capital N. The standard error of the mean tells us the uncertainty in our mean value, and this is what we usually report as the random uncertainty for our experiment. Graphs are absolutely essential tools in physics, are not they? They help us see the relationships between different quantities we measure. Now, when you are plotting your data, it is crucial to always include error bars on your data points. Think of these error bars as visual representations of the uncertainty associated with each measurement. They tell us the range within which the true value likely lies. These bars can extend in the x direction, the dry direction, or even both, depending on where your uncertainties are. Why are they so important? Well, they are crucial for judging whether your experimental data actually agrees with a theoretical model or a hypothesis. A good fit, meaning a line or curve that represents your data well, should ideally pass through most of these error bars. This visual check is often the first step in validating your results. When a result, z, is calculated from measured values x and y, which have uncertainties delta x and delta y, we use error propagation rules to find the uncertainty in z or delta z. For addition or subtraction, if z equals x plus or minus y, then delta z squared equals delta x squared plus delta y squared. So, delta z is the square root of this sum. For multiplication or division, if z equals x times y, or x divided by y, the fractional uncertainties add in quadratures. This means the square of delta z over z equals the square of delta x over x plus the square of delta y over y. Thus, delta z over z is the square root of that total. If z is x raised to the power n, the fractional uncertainty delta z over z is the absolute value of n times the fractional uncertainty delta x over x. Mastering these rules is vital for accurate results. Alright everyone, our main goal here is to measure little jig, the acceleration due to gravity. We are using the pendulum period formula. T equals 2 pi times the square root of L over g. Rearranging for little g, we get g equals 4 pi squared times L, all divided by t squared. This means we need to accurately measure the length of the pendulum, little l, and its period, little t. For step 1, measuring length L, we will use a meter rule. The main challenge here, and our primary source of uncertainty, is judging the exact center of the bob. Let us say our measurement for L is 0.755, plus or minus 0.002 meters. That 0.002 meters represents our estimated systematic uncertainty. For step 2, measuring the period et, we want to minimize random timing errors. So instead of timing just one swing, we will measure the time for 10 full oscillations and then divide by 10. To improve our reliability, we will repeat this measurement 5 times. Okay, let us look at how we process our timing data for the pendulum. We have 5 measurements for the time it took to complete 10 full oscillations: 17.4, 17.6, 17.5, 17.3, and 17.5 seconds. First, we calculate the average of these times for 10 swings, which gives us a mean of 17.46 seconds. Next, we find the standard deviation of these measurements, which is 0.114 seconds. This tells us about the spread in our data. Then, to determine the uncertainty in our mean time for 10 swings, we calculate the standard error. This is the standard deviation divided by the square root of 5, our number of measurements, resulting in 0.051 seconds. So, the time for 10 oscillations is 17.46 plus or minus 0.05 seconds, after rounding the uncertainty appropriately. Finally, to get the period t for a single oscillation and its associated uncertainty, we simply divide these values by 10. This gives us our final result for the period. T equals 1.746 plus or minus 0.005 seconds. Now let us tackle step 3, propagating the uncertainty for g. Our formula is g equals 4 times pi squared times L, all divided by t squared. Using the multiplication and division rule for uncertainties, the square of the fractional uncertainty delta g over g equals the square of delta L over L plus the square of delta t squared over t squared. For the t squared term, the power rule tells us its fractional uncertainty is 2 times delta t over t. So our combined uncertainty equation is the square of delta g over g equals the square of delta L over L plus the square of 2 times delta t over t. Plugging in numbers, g is 9.789 meters per second squared. Delta L over L is 0.00265, and delta t over t is 0.00286. This gives delta g over g as the square root of 0.00265 squared plus the term 2 times 0.00286 all squared, which is 0.0063. The absolute uncertainty, delta g, is then 9.789 times 0.0063, or 0.0617 meters per second squared. Finally, we round delta g to one significant figure, 0.06, and round g to the same decimal place. This gives our final result. G equals 9.79 plus or minus 0.06 meters per second squared. Often in our experiments, we are looking to see if there is a linear relationship between two variables. A classic example is Ohm's law, where potential difference V equals current I times resistance R. So, if you plot your measured potential difference against current, you should get a straight line. Now, how do we find the best straight line through our data points? We do not just eyeball it. We use a method called a least squares fit. Software packages like Python or Excel can perform this calculation for you. This fit is really powerful because it gives you the best estimate for the slope and the intercept of that line. More importantly for us, it also tells us the uncertainties in these values. In our example for Ohm's law, the slope of the V versus I graph directly gives us the resistance, R. So, a fit might tell us the resistance R is, say, 150.3 plus or minus 1.2 ohms. This is a much more rigorous way to determine our experimental values and their precision. Let us review some crucial practices for your lab work, and equally important, some common mistakes to avoid. It is vital to record uncertainties for all raw measurements. Always consider both random and systematic errors. When you combine measurements, propagate those uncertainties correctly. If you are graphing, use error bars. They are crucial. Report your final answer in the standard form. Value, plus or minus uncertainty, with units. And importantly, check if your result agrees with accepted values, considering your uncertainty. On the other hand, please do not ignore uncertainty. A measurement without it is incomplete. Be careful with significant figures, reflecting your actual precision. Understand the distinction between standard deviation and standard error. When drawing a graph, avoid drawing a dot-to-dot line. We are looking for physical models. Finally, avoid the generic human error excuse. If there was an error, describe it specifically and its likely effect. These guidelines are here to help you produce solid, reliable results. All right, let us wrap up with the main takeaways from our discussion on data analysis. First and foremost, remember that uncertainty is absolutely key. Every single measurement you take in the lab has an associated uncertainty, and this is essential for presenting a complete and meaningful result. It is not just about the number. It is about the range. Next, it is crucial to understand the difference between random and systematic errors. Know where your errors are coming from. Repeating measurements is a great strategy, but it primarily helps in reducing random error, not systematic ones. For your best estimate of a quantity, always use the mean of your repeated measurements. And for the random uncertainty associated with that mean, you will use the standard error. When you are combining quantities that each have their own uncertainty, you will need to apply the rules for propagation of uncertainty. Finally, always report your result with a properly rounded value and its uncertainty, and do not forget to include the correct units. These are the cornerstones of good experimental practice. Okay, that wraps up our overview of basic data analysis in the physics laboratory. We have touched upon why uncertainty is crucial, the different types of errors, and how to calculate and report your findings. I hope this provides a solid foundation for your experimental work. For those keen on mastering these concepts, I strongly suggest looking at John R. Taylor's An Introduction to Error Analysis. It is an excellent, comprehensive guide. Also, your university's first-year lab manual will be invaluable, offering practical advice directly relevant to your lab sessions. These resources can really help solidify your understanding.